Know what you're launching into. Know your peak lapse rate for the day. Know your perceived conditions before you drive out. Are you driving out for a sled ride? Or might you get your butt kicked? Life in the sky, where you wish to spend more of your time than being on the ground, rather than being on the ground and not really knowing what's in the sky. Wouldn't it be great to know the strength of the thermals of the day? Let's get started. Alrighty guys, let's get started. The idea behind putting this video together is so that you know your lapse rate, you know what to expect before getting out and driving out to the site. It's important that you have that kind of confidence. You can literally take this to anywhere in the world. It works everywhere, every country, every flying site. Okay, here you are taking a first look at the actual lapse rate numbers that you're going to be able to reference to before you go out flying. Here we have everything from a 0 all the way up to a 2.8 and what they mean and how they're going to relate to you, and then you're going to fly them and then you're going to come back. Anyway, we're going to get to that slide later. Let's get into the beginning of how to understand lapse rate. So if someone comes up to you and asks you, what is lapse rate? You will now be able to tell them, air cools as we go higher. It's quite simply that easy. The question is, how much or how little does the air actually cool per 1,000 feet as we go higher? And I know some of you are asking, so why would we need to know our lapse rate and how do we measure it? Yes, two excellent questions indeed. Let's also take a look at thoughts about thermals before driving out to the site. Will it grow strong enough to stay up, or will it be a sled ride? Will it be a really strong day? Will it be nice to thermal a bit? Maybe do a cross-country flight, but maybe not also have it be too strong. Now, wind is also a factor in your conditions, and it is to be looked at as well. There is coastal site information versus inland site information. There are various rules as to what is acceptable and safe and what is not. This will be covered in another video coming up shortly. Now, the big question is, what is the difference between the temperature at 6,000 feet versus the temperature on the ground? This is the area that we most commonly fly in, is between 6,000 feet and the ground. Okay, for our first example, as you can see here, we're going to say that at 6,000 feet it's 8 degrees, we figured that out, and on the ground it's 20 degrees for our first example. Now I'm going to show you where you can find that information shortly, but let's carry on with this for an example. Okay, here we have the ground temperature. Take away the 6,000 foot temperature equals your temperature difference. Let's get more into detail on that. Okay, so we have 20 degrees, take away 8 degrees is 12 degrees. That is your temperature difference. Okay, now we're going to take that temperature difference and we're going to divide it by 6. Why do we do that? Because we want to know how many degrees per 1,000 feet we are dealing with here. That will be your lapse rate. So we are dealing with a 6,000 foot distance and we want to know how many degrees per 1,000 feet it's cooling. Okay, so for this example, in this case, we have 12 degrees divided by 6 is 2, and on this day, your lapse rate is a 2. Okay, for this next example, we're going to bring that 6,000 foot temperature down a bit. We're going to lower it down to 5 degrees Celsius, and of course our relationship will now change between the ground and 6,000 feet. Our new equation looks like this. So we have 20 on the ground, 5 degrees at 6,000 feet. 20 take away 5 is 15, and then we can quickly go to 15 divided by 6, and we want to know how much it's cooling per 1,000 feet, and here it is. Okay, so you get the idea. On this day, your lapse rate on this day is at 2.5. Okay, let's just do one more example here for you. We're going to change that 6,000 foot temperature to 7 degrees, and let's find out on this day what your lapse rate would be. So we've got 20 on the ground, take away 7 at 6,000 feet is 13 degree difference. That 13 degree difference divided by 6 for 6,000 feet equals... I think you get the idea. Okay, so you already know this, but I'm going to give it to you anyway. Your temperatures are available by doing a calculation from information on the internet. Okay, so when you get out there and you're traveling or your local sites, get your ground temperature and get your 6,000 foot temperature. We use the RASP. AWWS flight planning is fantastic for that. And also windy.com will give that to you as well. So when you're doing your searches, go and look at the area where you're able to get the ground temperature and the 6,000 foot temperature for that exact area. Even if it's not right on your site, it's going to give you a pretty good idea as to lapse rate for the day in that area. Okay, for our first example, we're going to do Vancouver Airport. So we're looking for Vancouver after we search AWWS flight planning. Once you get to that site, click on the button. Second button over you can see there is called upper winds. That's the one we want. And this reading works very true for pretty much the entire Fraser Valley during all times of the year. Once you click on that, you'll get to this next page. You'll see that button called Pacific. Go ahead and click on that. And after you've clicked on Pacific, it's going to bring you to this next page. Look down towards the left, you'll see Get the FDs, and that's the next button you're going to click. And then scroll down on the next page until you get to Vancouver. I'm going to share all the detail as to what this is on this site later, but right now we're going to go look at just a couple of things. Okay, so we're looking at the area that says for use. It used to be called Greenwich Mean Time. This area that we're talking about is also referred to as Zulu time, but today they call it Universal Time Coordinated, otherwise known as UTC. Okay, so we're looking for the time that we will be flying, and in this case, we're going to focus on that 21. You're going to take off 7 hours on average, whether it be daylight savings or not. It could be 7 hours or 8 hours. Okay, but for this example, we're going to take 7 hours off of that 21, which brings you down to 14. So 1400 is what that turns into, which essentially is 2 p.m. That next number we're looking at is 06. That stands for 6 a.m. Now we're going to take 7 hours off of that, and that puts us at 11 p.m. or 2300. So this is the time slot we want to be looking at because that is the time period in which we are going to be flying in this case between 2 p.m. and 11 p.m., but we'll land far before that because of visual flight rules, of course. Now we're going to look at the last two digits on that line, and you can see that it says -5. Okay, so that means it's in the negative temperatures. We need the total distance from the ground temperature to the 6,000 foot temperature. So we're actually going to add this number to the ground temperature. It's also important that you notice that I'm referencing to the 6,000 foot heading and I'm taking the information under that. So if this number was not a minus number, we would subtract it. In this case, we're going to add it because it is a minus temperature. So there you go, 6 plus 5 is an 11-degree difference. So now, again, the exciting time. What is our lapse rate? 11 divided by 6 is 1.8 Celsius per 1,000 feet. So there you go. Yep, 1.8. It's a sled ride. Okay, so for on this next slide here, I want you guys to maybe take a screenshot of this or stop the recording right here and write notes down as to what I've got for each one of these numbers, and then I want you to decide how it feels for your site. So it could be completely different than what I've got here based on the amount of rock exposed. We're going to get into all of this in the next short while. Basically, what I want you to take away from this is that, of course, when you have a 0 up to a 2, you're dealing with pretty light conditions. Over top of a 2, yeah, you know, you can stay up. You're going to be able to enjoy some height. You're going to be able to stay in the air longer than an hour or two. When you get up towards the 2.8, yeah, you're going to experience a lot more lift. It's going to be a lot more punchy. The thermals are going to have a sharper edge. Now let's look at the strength and the height expected of the thermal based on the peak lapse rate for the day. This is just a generalization so that you can get an idea as to what to expect on your calculation. There are many other factors that we will look at later, like wind, dew point, inversions, and times of day. We want to know the strongest part of the day so that if it appears to be a strong day, then we have that option to launch early if we want, before it gets really strong. Okay guys, we're going to start with the standard adiabatic lapse rate. Around the entire world, the average is 2 degrees per 1,000 feet. So if we go down to our example here and we see 20 degrees, we're going to take away 2 degrees from that and we get 18. Very good. We're going to keep on cooling at 2 degrees per 1,000 feet all the way up to 6,000 feet. And much like in the example before, 20 degrees on the ground, 8 degrees at 6,000 feet. You know the difference between this now. This is a visual of the air cooling at 2 degrees per 1,000 feet. Now let's take a look at how to figure out the height and the strength of the thermal. The first thing we're going to need to do to figure this out is to figure out the dry adiabatic lapse rate. You can see in the bottom right hand corner there the -3 -3 Celsius. Yes, the thermal itself cools at 3 degrees per Celsius. Hang on to that. Okay, so we're going to take that 23 degrees and we're going to cool it 3 degrees and we get 20 degrees. And so on and so forth. Cooling at 3 degrees per 1,000 feet, all the way up to 10,000 feet. Okay, now it's time to make another really important point. Your thermal needs to be 3 degrees hotter than the surrounding air to trigger off. That's almost worth saying again. Your thermal needs to be 3 degrees hotter than the surrounding air to trigger off. Hang on to that. All right, let's keep going. Okay, you can see that your thermal is 23 degrees and your ground is 20. So the thermal triggers off and goes up. Now, we take a look at the next level. We're now up to 1,000 feet. The question is 20 degrees warmer than 18? Yes, it is. So what happens? The thermal then keeps climbing to the next level. We are now at 2,000 feet. Is 17 warmer than 16? Yes, it is. The thermal keeps going up. Oh, look at that. Okay, so at 3,000 feet, the thermal is the same temperature as the surrounding air. That means the thermal no longer has power to punch up because it is now equal temperature and equal pressure. So based on this calculation, on a 2-day, you can expect your thermals to go up to 3,000 feet. Yeah, okay. All right. Well, let's do another one. Let's do another one where we are dealing with a 2.5. How about that? Okay, let's do that one. Okay, so we're going to have the same ground temperature at 20 degrees, but this time the air is going to cool 2.5 degrees per 1,000 feet, and then we're going to see how high the thermal climbs based on equal temperature, equal pressure at height. And if we notice, hey, look at that. We have equal temperatures at 6,000 feet. Again, the important point to be made here and the thing to hang on to, the idea to hang on to, is that the thermal is continually warmer than the surrounding air, and that's why it's climbing and that's why it's going up. Because until the pressure and the temperature are the same, the thermal will keep climbing. Hang on to that. So, on a 2.5 day, we can expect thermals to climb to 6,000 feet. Now, these examples will change based on how much sun is hitting the ground, how much rock is exposed, how much cloud there's in the sky, and of course, if there's an inversion or not. But we're not going to get into that. We're just giving you the basic idea on how to measure the strength and height of a thermal. Okay, for our next example, we're going to do a 1. So our surrounding environment is a beautiful, bright, sunny day, and the air is only cooling in our environment at only 1 degree per 1,000 feet. Let's take a look at this one now. Okay, our now environment is cooling at only 1 degree per 1,000 feet, so 23 is warmer than 20, 20 is warmer than 19, but 17 is not warmer than 18. On a 1 day, we can expect our thermal to go a little bit more than 1,000 feet. Not much for cross country, but excellent for the brand new pilot. For the brand new student, this is perfect. The question did come in, what is environmental lapse rate? Well, that's any lapse rate that's not your standard adiabatic lapse rate. Okay, so your standard is a 2, anything else other than that is your environmental. Alrighty, let's get into doing a 2.8 day. The environment is now cooling at a minus 2.8 degrees Celsius per 1,000 feet. This is a big day. This is a cross-country day. This is the day where you're going to hear guys going 200 kilometers doing the triangles. Absolutely. We don't get them often. April, May is our big 2 months for that in the Fraser Valley. So, let's take a look here. Okay, so at 6,000 feet, it appears that thermal, being 5 degrees, is still hotter than the surrounding air at 3.2 degrees. That means the thermal is going to still continue to climb. A matter of fact, that thermal climbs so high that it actually goes above 10,000 feet in this example, because the 10,000 foot thermal temperature is still warmer than the surrounding body of air it's in. Now, there's a really important point I want to make here, guys, is that on the the coast of Western Canada, the Fraser Valley and surrounding areas, we have a very moist atmosphere, a very moist environment, as you will. So when those thermals are going up, they primarily hit dew point before they're realized for their full potential. Okay, but if you go inland, whether it be Lumbee or maybe Australia or other parts of the world where it's away from the ocean, it's a much drier climate, you can still have a smoking hot lapse rate, but you don't see the cloud because it's a much drier environment. The lapse rate is still reaching great heights, you just don't have that visual to reference with it. So this becomes extremely important, especially when you're traveling to new environments that you've never flown in before, because now you're going to take on a whole new responsibility and a whole new understanding and a whole new respect for what lapse rate is really all about. Okay, here's your test, guys. If these are your lapse rate numbers, how do you get them? Obviously, you can go back to the beginning of the video and watch it again, but you really want to commit this to memory and you want to get good at it. So go ahead and test yourself even on non-flyable days. Okay, another component of how much your lapse rate will be realized is how much sun is hitting the rock and how much rock is exposed. So, on some sites, you're going to find a lot of green. Other sites, you'll find a lot more rock, okay, in combinations of. This also plays a part in how strong your lapse rate will be realized. Okay, so on a good lapse rate day in Golden, BC, it's going to be real easy to get to 12,000 feet. Lots of rock, good lapse rate, away you go. Alright, now let's take a look at Woodside Mountain. Keep in mind, a 2.1 at Woodside is going to be way different than a 2.1 at Golden for those exact reasons I just explained. Alright, Lumbee, another site in BC. A good example of a fair amount of rock, a fair amount of green, and it's a drier environment, so thermals are going nice and high, and a 2.1 here will feel different than a 2.1 at Woodside or a 2.1 in Golden. The last site I'm going to reference to in this presentation will be Manila, Australia. If you can, you absolutely have to get over there. It's an amazing flatland cross-country site, and it's really easy to get good and high. They've got fantastic lapse rates, and if you're not quite getting what you want in the shaded areas, just go back into the sun and enjoy yourself. There's lots of examples of green and dirt everywhere. Another thing I want to mention just before we get to the end of this video is that just because you see a field does not mean that it will be a great source for a thermal. It depends on how watery that field might be. So keep in mind, if it rains in your area, and you've had rain in the last few days, as you're driving out to the site, take a look at those fields and make sure you know that if you can rely on them for being dry, great, but if they're wet, they're probably not going to be a very good thermal generator. Therefore, the lapse rate that you've figured out may not be fully realized for the full strength of that predicted lapse rate. Okay, so in your logbook, log your lapse rates versus the sites you fly over the period of a year. Then go through your logbook and compare all the different sites with the same lapse rate and different lapse rates. Then compare all of the different lapse rates for the same site that you fly. You'll be excited to see the difference and feel the difference. Now, after about 8:30 at night, I believe they changed the forecast for the AWWS site, and that very bottom row will actually give you the next day's reading. So again, take the time slot on the bottom, and of course you know how to take off the 7 hours now to give you an example as to the time that you're looking at, and then figure out your lapse rate for tomorrow. So once you have tomorrow arrive, you can refigure it out again and see how close they still are to their prediction. Alrighty, guys and gals, go ahead and figure out your lapse rate for the next day. Go ahead and fly your lapse rate, and then come back and leave a comment in the section below. I'd love to hear how close I am in regards to the predictions I've made for my numbers in regards to what you get from your numbers. Alright, have a great time, and we will see you out there.